Hi folks, welcome to another video. In this one I'm going to be going over the gravitational field, lesson 1 from my little book about fields. This video is going to cover almost all of D1 in the new IBDP syllabus. I'm also going to be solving some exercises along the way. So these are all the things I would normally say in a classroom setting. But now students have this video to refer to if they want to review things, if they want to learn at their own pace at home, then here you go. So this is going to allow me to flip my classroom a little bit, and I can spend more time on problem solving when I'm with my students rather than just covering material, which students really should be sort of learning on their own when they sit and read the text. So even though this is a video, I'm sort of going over the content of these notes, I still recommend students to read the notes. Nothing really beats reading. Your mind does magical things when you are sitting down quietly on your own reading a text. So try and also read this on your own. Okay, let's get started. Okay, we're going to start off talking about contact forces. So if I want to push a block across a table, of course my hand needs to be in contact with the block and I need to exert a force on it. But am I really touching the block? If we were to zoom in on the surfaces of my hand and the block, at a nano scale level, we'll notice that they're sort of separated by a small gap of empty space. Then in fact not touching. What's really happening is that the electric charges in the molecules of my hand, they're exerting electric forces on the charges in the molecules of the block, and that's what is making it move. It's like two magnets of similar poles that you try and push together, but they can exert forces on each other without actually touching. And at a fundamental level, all contact forces are like that. They're due to sort of non-contact electromagnetic interactions. And another example of a non-contact force is in fact gravity, which we know so well. If you've ever thought about it, how does Earth actually exert its influence on objects? Objects fall to the ground without actually being in direct contact with the Earth. The sun obviously can keep all the planets nicely in orbit without any strings attached. So, there's this action at a distance going on, and how do we make sense of that? And the answer is to view forces as manifestations of force fields. And that's a very fundamental concept that plays a very central role in modern physics. The idea of a force field was introduced by Michael Faraday in the 1850s, and he used it to explain all these electromagnetic interactions that he was investigating. It's worth noticing that fields are real physical quantities. They exist independent of measurement. They occupy space. They can store and transfer energy and momentum. They can affect the geometry of space-time, etc. It's a very, very important idea that we are looking at here. So we're going to investigate the gravitational field. So first concept here is to introduce what's called the gravitational field strength. So let's first review Newton's universal law of gravity. We know that it states in words that every point mass m exerts an attractive force on every other point mass m along a line joining their centers. The force is proportional to the product of the masses and inversely proportional to the square of the distance between them. They don't really have centers because they're point masses. I need to take that out. Okay, but you know that here's the mathematical expression for that. Should be familiar with this. Big G is the gravitational constant, has this value as you can see. Okay, so this law says something about point masses, but it turns out you can show that any object that has a spherically symmetric distribution of mass, like planets and moons, they exert the same gravitational attraction on external bodies as if all the object's mass were concentrated at a point at its center. So important to know that Newton's universal law of gravity kind of applies to planets and moons, where we just have to take the distance from the centers of those objects. So how do we understand gravity in terms of the field concepts? Well, we just need to adjust our perspective a little bit. So imagine little mass m being removed, okay, and think of the big M as creating this invisible field surrounding it. And so there's actually something there, right? At any given point in space-time, there is a field present. Even though there are no other masses there, there is still a field. And we know it's there because if we were to place another mass at a point in the field, then it will experience a force according to Newton's universal law of gravity. So what we are doing is we're associating with each point in the field a vector quantity called the gravitational field strength vector, little g. And it has a magnitude that is equal to the gravitational force per mass at the point. And the direction of that vector is equal to the direction of the gravitational force at the point. So, easy to calculate the magnitude. We take the force on a little mass at the point, divide out the mass of that we placed at the point. Okay, so you can see little m cancels out there. And you can see the direction points towards the center. So here we have a picture of the gravitational field strength vector that has been drawn at a point in the field. You can see it's very similar to what we saw up here. We just removed the mass m, and now we have drawn a vector that is the force per unit mass at that point. And we call this a vector field. So the gravitational field is an example of a vector field because there is a vector associated with each point in space-time. It's worth mentioning we can also talk about scalar fields, and that's just fields that are described by only having a scalar associated with every point in space. For instance, temperature in Earth's atmosphere. That's an example of a scalar field. So every single point in Earth's atmosphere has a certain temperature at a given point in time. That's a scalar field. Okay, let's try and do some exercises. Okay, so the first exercise is to work out the unit of g. And as you can see, g is a force over mass, so it's pretty obvious that the unit is just newtons per kilogram. Then we have to express it in base SI units. Okay, we know Newton is not a base unit. The Newton comes from kilograms times meters per second squared. F equals ma, mass times acceleration, over kg. Kg cancels out. And you can see that, the unit is in fact also meters per second squared. And what other physical quantity has that type of unit? Acceleration, of course. So we immediately notice that, g has the same units as acceleration, and that's not a coincidence. We can think of g as the acceleration due to gravity at that point. Let's work out the magnitude of g at the surface of the Earth. Okay, so how do we do that? Well, magnitude of g is big G m over r squared, where that m is the mass of the Earth, r is the radius of the Earth. So let's plug everything in, shall we? 6.67, 10 to the negative 11. Mass of the Earth. Radius, but it's in kilometers. Let's convert it to meters. Okay, don't forget that. And it's squared. That's a common mistake that students make. Forget that. Units and squaring. Okay, so I'm typing along. You guys should be typing along on your calculators too. Get the experience of working this out on your own. Very important. Okay, I got 9.8 meters per second squared, or 9.8 newtons per kg. Those units are the same as we saw before. Okay, so that's not surprising, of course, that at the surface of the Earth we have an acceleration due to gravity that is 9.8, or we have a gravitational field strength that is 9.8 newtons per kg. That was exercise 2. Exercise 3. So what's the magnitude of G at a point that is 2 Earth radii away from the center? Okay, well, we can look at the calculation we just did, and we can imagine R replaced by 2R. Okay, can you imagine that? So, we're working out this. But I don't need to plug everything in again, because I know that, that's going to really be 1/4 gm over r squared, and gm over r squared was what I just calculated before, but now it's 1/4 of that. So let me work out 1/4 of what I just have on my calculator. That's 2.4. Okay, so that's 2 Earth radii away. 3 Earth radii away. Probably just have to divide by 9, as you can see. 1/3 squared, 1/9 of that. And that is going to be, where should I write that? Okay, let me quickly write it up. 3 Earth radii away is 1/9 of at the surface, and that is 1.1 Newton per kg. You can see G decreases as we move further and further away from the Earth. Okay, so you can see I've got the graph of gm over r squared here below, and we can just go to the Desmos file and quickly answer the question. So we want to use the graph to read off G at 20,000 kilometers. Now, the unit on the x-axis is in meters here, right? Okay, so 20,000 kilometers, 210 to the 4 kilometers is 210 to the 7 meters. So you can see 2 times 10 to the 7 meters. You can see we are around here, right? So I can read off that's around 1, okay? 1 newtons per kg. So we can go back. Here we go. So we can read off that G is around 1 Newton per kg. Not surprising, because 20,000 kilometers is around 3 Earth radii. So of course it's close to what we got before. What does G approach as you go farther and farther away? Well, obviously it approaches 0, as you can see. And that's obvious to everyone, I hope. What does the blue line indicate? What do you think it indicates? Do you think you can see the value of G at that blue line is around 10 newtons per kg? Yes, you're right. It is the radius of the Earth, right? We're at the center of the Earth at the blue line. And does it make sense to continue the red graph to the left? Not really, because then we're going into Earth. So that's not really what we want to be doing. We are just looking at the influence of, we're looking at Earth's gravitational field outside of its surface. Although you could actually theoretically start working out, well, what if we drill a hole through the Earth? How does G change as you move through that hole? That can be worked out, but that's going to be another problem that we work on later. Okay, exercise 7 is just drawing field strength vectors at different points. So we're looking at the Earth here, points that are 1 Earth radii sort of away from each other. And I'm going to use a scale of 1 Newton per kilogram equals half a centimeter. So I know that on the surface of the Earth, where G is around 10, then it's going to be around 5 cm long. Is that correct? Yeah, times 10, 5 cm. Good. So I can draw some G vectors, draw them to scale, to that scale. Okay. And then if I go 2 Earth radii away, G is only 2.5 newtons per kg. So now I need to take 2.5 times 0.5, that's 1.25 cm. So now at these points, the lines are only 1.25 cm long. So they look roughly like this. Okay. Got the direction pointing towards the center of the Earth. and I've got a correct magnitude. Okay, if we're 3 Earth radii away, then G is around 1.1, roughly 1, which is only half a centimeter. So they're really short now. As we move further away, the gravitational field gets weaker. When I'm 4 Earth radii away, it's only 0.6 newtons per kg. And that is how much? 0.6 times 0.5, 0.3, just 3 millimeters. Very short one. There you go. Okay, so this is how we can visualize a gravitational field. We can simply just draw field strength vectors at any given point. Okay, then there's another way to visualize a gravitational field, and that is by drawing something called field lines. Now, a field line is related to the field strength vectors in the following way. So the field strength vector is tangent to the field line at any given point, and they point in the same direction. So how do we do that? Well, let's go onto this drawing, and we basically just draw lines, and these lines are such that the field strength vectors are tangent to these lines at any given point. Okay, and they point in the same direction as the G vectors. So there you go. That's another way of visualizing the field. We draw what's called field lines. Notice that when the field lines are closer together, then the gravitational field is stronger. When the field lines are further apart, then the field is weaker. Okay. So the field line model is quite a useful way of visualizing fields. It has its limitations, but it's pretty useful. For instance, if we look at these pictures over here, you can see, okay, a nice radially symmetric force field surrounds the Earth. We can see that if I go a little bit closer to the Earth, it looks like this. And if I'm really close to the Earth, then we actually have a constant gravitational force field. That's when G becomes constant, right? And we just have lines that have an equal, they're an equal distance apart, because the strength of the force field is approximately constant. Also, you can see if you were given a picture of field lines looking like this, then you'd be able to know that, oh, it looks like there's some very massive object, some object that's more massive than the surrounding ground. At that point, you can see the field lines sort of bending slightly inwards, creating or also suggesting there's a stronger field close to that more massive object. Okay. Exercise 9 is really important. We're talking about what's called the principle of superposition. So it's a very significant experimental fact that when more than one field exists in a region of space-time, then the fields, they combine to give a net field, according to this principle of superposition, that the net gravitational field strength vector at a given point is the vector sum of each individual field strength vector at that point. So we're going to sort of make sense of that, solving this problem, which is a past IB exam problem. And we're looking at this figure here where we have a planet and 2 stars. The planet has the same mass as Earth. The 2 stars have the same mass as our Sun. There's a distance given between the stars. They also tell us how far away the planet is from each star. And the planet is sort of equidistant from each star. Okay, so a lot of information we need to sort of digest there. First of all, just on the figure, draw 2 vectors to show the gravitational field strength vector at the planet's position due to each of the stars. Okay, so basically here we just need to say, okay, well, at the planet's position, there's a vector, field strength vector due to 1 star on the left, and at that point there's also a field strength vector due to the star on the right. There's sort of like a G1 vector and a G2 vector. And those two fields, they superpose. And what does that mean? Well, it means that to get the net field strength vector at that point, we just need to add these two vectors. So we need to use vector addition. Luckily, we know how to do that. So this net G field vector is the sum of those two vectors. You can see it's pointing straight down, has that magnitude as indicated, and we've done the first exercise, just drawn two vectors, right? We're actually on our way to solving exercise B here. Calculate the magnitude and state the direction of the net field strength vector. Okay, direction is straight down, as you can see, but the magnitude, how long is that arrow? So let's try and work that out. We can first work out the magnitude of each of the field strength vectors, because that's going to be Gm over r squared, right? So we've got big G, we have one of the stars, 30, 2 times 10 to the 30, I believe it said, yep, kg, divided by, and then the distance, the planet that is 6, 10 to the 11 from each star. 6, 10 to the 11, and we have to square that. So we can work out the magnitude. Let's do that carefully. E to the 11, was it squared? Okay, got lots of big numbers here. Roughly 3.71. Let's round it off like that. For now, we're going to be using this in a further calculation. What's the unit of G again? It was newtons per kg. Okay, but we want to find the magnitude of G net, and how do we do that? Well, we kind of, two approaches. Use similar triangles or work out the angle. Maybe we can just work out the angle here, because if I know the angle theta, then I can find the sort of vertical component of each G, and then I can just multiply by 2. So why don't we take that approach? Centers are separated. Yeah, okay, good. So we know that this distance was 6, 10 to the 11 meters. I know that this distance down here is, 3.4, 10 to the 11. So I can get the angle by doing sine, right? Sine theta is the opposite over the adjacent. So we get sine inverse, 3.4 divided by 6. And that is 34.5 degrees. Okay, and then now I can say, okay, G net, magnitude of that, it's going to be 2 times cosine of the angle times the magnitude of one of those G's. Yeah, which I'll call G. So I'll just write that slightly differently. So it's G times cosine theta, and 2 of those. So I plug in 2 times 3.71, 10 to the negative 4, times cosine 34.5. So let's do that. 2 times 3.71. Do this on your calculators as well. Pause the video, work it out. And I got 6.1 times 10 to the negative 4 newtons per kg. There you go. That's the magnitude of the net gravitational field strength at that point. Calculate the magnitude and state the direction of the net gravitational force on the planet. Okay, well, if I have the gravitational field strength, right, then in order to do C, where I need to calculate the net force, I just do mass times G net. And the mass is given to us times the net G. So let's do that. 6.1 sorry, that was to the -4 there, times 6e24. And this is going to be around 3.7 10 to the 21 newtons. Okay. Get the net force by just taking the mass times the net field strength, just mg. It is just, kind of the weight formula, just using the weight formula in this more sort of complicated scenario. D says write down the acceleration without any further calculations. Well, you all knew that, well, you could, I guess, calculate, the net force, the mass, divide by the mass, but wait a second, we don't need to do that because we already have the acceleration, the g net. G is really just an acceleration. Remember, newtons per kg is meters per second squared. So I know that the acceleration of that planet is going to be 6.1 10 to the -4 meters per second squared. Okay, in exercise 10, we can see the net gravitational field of the Earth and the Moon, and some of the field lines have been drawn. And we have to draw some field strength vectors at various points. So let's try and do that. So for instance, here's a point. And we know that the field strength vector is tangent to the field line. So it has to sort of be in this direction. Now at this point, the gravitational field from the Earth is actually stronger. So we're going to have a g vector pointing sort of towards the Earth along the tangent. So I'm going to draw that like that. If I take a field line, or if I look at a point that's relatively close to the Moon, for instance this point, then we're going to have a field vector again that's tangent to the field line, and it's going to probably point in this direction. If I go a bit closer to the Earth, say at that point, okay, I'm going to have a field strength vector like this. It's much longer than the other ones because it's closer to the Earth where the field lines are closer. So that's how that works. Why are they warped like this? Well, we know that these field lines, they represent the net gravitational field of these two fields. So we need to add the separate strength vectors from the Earth and the Moon at every point. So we're doing vector addition at every single point. That's why the field lines sort of look like this. What do you think the yellow dot and the yellow dashed line represents? Okay, so the yellow dot here, this is actually where the field strength from the Earth and the Moon cancel out. Okay, so it's like the net G is 0 at that point. Net G is 0. So in theory, I could place a little mass there and it wouldn't move. It's equally attracted to the Earth and the Moon. And at all other points on the yellow line, the separate G vectors have a same magnitude. It's like G1 from the Earth, G2 due to the Moon. They have the same magnitude at all points on the yellow dashed line. But it's only 0 at sort of right in the middle between Earth and the Moon. Imagine a straight line joining the centers of the Earth and the Moon. We have to sketch how the absolute value, the magnitude of G net varies. Okay, so imagine this line, and let's sketch a graph. So it's the magnitude, it's always going to be positive. So we sort of start at some point on the surface of the Earth. We're going to start on the surface of the Earth again, not inside the Earth. And we know that G is around 10 at that point. Okay. Then as we move away, it's going to be decreasing until we kind of reach that point we were just talking about where G is 0. The net G is 0. And then as we come closer to the Moon, starts going up again until we reach the surface of the Moon, where G is only around 1.6 newtons per kg. And this is roughly what G net magnitude looks like. Now, we can go check that out on Desmos, right? So we can go to Desmos, have a look what it looks like. So I graphed it carefully here, and you can see that looks roughly right, although it has sort of a funny shape at that point. And that's because if we, instead of graphing the magnitude of the net field strength vector, if I sort of graph it with sign, it's a vector quantity, right? So if I don't graph the magnitude, but take into account the direction of G, so it's like positive when it's pointing towards the Earth, and then it's negative when it's pointing towards the Moon, we get this nice curve. And you can see how we get this nice point where it's sort of, G, we start on the surface of the Earth, G decreases, and then it becomes 0 at this point, and then it starts becoming negative because now it's pointing towards the Moon, and that's a nice graph. Okay, let's move on with concept number 2, gravitational potential energy, the general formula. So quickly to revise the concept, we've seen the formula mgh before. We talked about how if you lift something up in the gravitational field close to the surface of the Earth, where g is constant, well, you know that the force of gravity is mg, and if I'm pulling it upwards with a constant speed, then my pull force also has the magnitude mg. And if I'm pulling it upwards, the displacement is upwards, I'm doing a positive amount of work on it, mgh, and that is going to be the energy stored in the gravitational field as potential energy. And I can, if I let go of it again, then all that energy is going to be converted into kinetic energy, etc. So that's what we have talked about. It's a rather abstract concept. Remember that energy is quite abstract. It was only invented in the 1800s after Newton's death. So Newton, he never worked with the concept of energy. Okay, but what happens when we try and lift this object very far away from the Earth? Because then the value of g is going to be changing. So how do we sort of work out the amount of work done on that object as g is changing when we have sort of a continuously changing quantity and we need to kind of add up its effect? Then we need calculus, integral calculus. So even though this is a non-calculus course, it's still worthwhile going over the derivation because you will eventually learn calculus, and it's a very important sort of way of thinking in physics that you need to become comfortable with. So here we have a picture showing us a mass m that starts at a certain distance r away from this planet, and there's an amount of force acting on it, gmm over r squared, and we can imagine that something is lifting it outwards with a constant speed, applying the same amount of force on it all the way to infinity. And we're going to define the potential energy to be 0 at infinity when these two masses are infinitely far away from each other. Remember that the reference point for where the potential energy is 0 was ours to choose, also an mgh. We sort of had to pick a reference point, and that's because it's only the change in energy that's relevant, not the absolute value of the energy at a given point. So that's important to remember, that potential energy is 0 when the masses are infinitely far away. So how to calculate the total amount of work done in pulling it away to infinity? Well, we imagine the path broken up into lots of small segments that have a distance delta r, and if those small segments are small enough, the force is approximately constant. So we can use the work expression, force times displacement, over these small segments. And when we move on to another segment, the force increases a little bit. Move on to the next segment, the force increases a little bit, or actually it decreases, I should rather say, because we're moving further away. Just to kind of show you the graph of that, of course, we can see how the force changes with distance, graphing gmm over r squared. And we know that work is the area in a force distance graph. So we're basically trying to work out the area that is shown here in blue. And that requires some calculus to work out what it is. And the total work is adding together all those small contributions of work. It turns into an integral, and it looks quite scary if you don't know integral calculus, but it really isn't. And you'll soon be able to calculate this. And it's a small calculation, but basically the area below that curve turns out to be gmm over r. So that's this blue area, gmm over r. And that's the total amount of work done in pulling the mass out to infinity. So if the potential energy at infinity is 0, and we sort of added this amount of work to take it up to 0, then it had to be less than 0 when it was at a distance r away. And we simply just take away this amount of work from 0 to get the potential energy at distance r. So you get this formula showing us that the potential energy is negative when those two masses are sort of bound to each other, when they're close to each other. We have this amount of potential energy in that system. And it's only when they're infinitely far away from each other that there's 0 potential energy. It sometimes confuses students that this energy is negative, but remember, in the MGH case, it could also be negative, all depending on where your reference point is. Okay, so let's work on some exercises. Okay, before we do the exercises, let me just stress and emphasize that this new formula we have worked out really is the generalized version of MGH. So whenever we are dealing with planets and moons in orbital motion, we have to use this expression for the potential energy and not MGH. You might think that these two formulas look very different and how can they possibly have anything to do with each other, but in a later problem I'll show you it's quite easy to see how one leads to the other and so on. So let's just keep going with the exercises. First one, calculate the potential energy of a 1 kg mass on the surface of the Earth. So this is just a direct application of our new formula. So we basically need to work out this, need to plug in all the numbers. G, which you should know by heart by now. Mass of the Earth, you really also should know that by heart, but okay, you're not required to. 1 kg, and then the radius of the Earth, and we do not square it. Okay, remember, don't make that mistake. Yes, it looks a lot like the force formula, the gravitational field strength vector formula, but this is the energy formula. Do not square it. And when you plug in all the numbers, you get something like 6.3 10 to the 7 joules. Okay, so it's energy, remember, so it comes out as joules. Okay, now let's calculate the potential energy of the Earth-Moon system. That is another direct application of the formula. But now we don't have a 1 kg mass at the surface. Now we have the moon long distance away. It's again just minus gmm over r. Have to plug in the numbers correctly. Mass of the Earth, okay, mass of the moon. It says to use 7, 10 to the 22. The moon is roughly 100 times less massive than the Earth. And the distance between their centers, which is what we use, it's in kilometers, convert to meters, and remember again, don't square it. And the answer gives us negative 7.3 times 10 to the 28 joules. Okay, number 3, we have to graph the variation of potential energy with distance. Okay, let's do that. So we're graphing potential energy, which is negative. So, and it's a 100 kg mass that starts at the surface of the Earth. So 100 kg is 100 times more than the 1 kg mass in exercise 1. So we can just multiply that by 100 and we get negative 6.3 times 10 to the 9. So let's just write the units here as 10 to the 9 joules, so I can just write negative 6.3 on the axis. That's where we start, and then we know that the potential energy is proportional to 1 over r, so it sort of increases as a 1 over r relationship, and that's a hyperbola. Maybe you've come across that in math. It's the reciprocal function, y equals 1 over x, and here's just negative 1 over x. That's what the variation looks like, and that's the name of the curve. Okay, exercise 4. So what's the change in gravitational potential energy when a satellite of that mass moves like that? Okay, so here we have to look at the change in potential energy, which is the final energy minus the initial energy. The final energy is when it's at 5 Earth radii minus when it was at 2 Earth radii. Now be careful with the negative signs there. We can also take GMM over R outside of a bracket. We get this, and need to plug in the numbers. When you plug in all those numbers carefully, you get 4.7 10 to the 10, if I did that correctly. And that's a positive increase in potential energy because it's moving further away from the Earth. And if it had been going in the opposite direction from 5 Earth radii to 2, then we would get the same amount, but it would be negative. The potential energy decreases when we come closer to the Earth. Okay, exercise 5 is sort of a technical exercise. Does the work done by gravity when a mass moves between 2 points depend on the path taken? Maybe you can remember from when I derived mgh that the work done by gravity does not depend on the path taken. That makes gravity a conservative force. That is why we can actually define a potential energy function. So it's the same in this more generalized case. And maybe I just want to quickly show you sort of why that's pretty obvious. So here we have, say, a planet, say the Earth. And if we imagine we start at a point A and we want to go to a point B, then you could ask, well, the work done by gravity in going from A to B, does that depend on the path taken? Well, let's look at one path. Let's look at a path that starts at A, moves out radially till it gets to this point, and then it moves along a circular arc up to B. So it's like outwards and then moves along a circle. Then let's talk about the work done along this path. So in the radial section, when it's going outwards radially from A to this point C, then work is being done by gravity. We can use calculus to calculate that. But then when we move from C to B along the circular arc, then the force of gravity is always going to be perpendicular, pointing towards the planet, perpendicular to the displacement. So gravity does no work along that section of the path. So it's really only the work from A to C that matters. And any path from A to B can be approximated to sections that are radial and circular. So for instance, I could go to the left along a circle, radial outwards, circle, radial outwards, circle, radial, and so on. And it's only along the radial sections, like the ones moving radially outwards, where work is done by gravity. And again, you can see that is going to be the same work done from A to C. So the work done in going from A to B only depends on kind of this radial distance between A and B. So that is also why, okay, even gravity, even in this generalized case, is a conservative force, and we can define a potential energy function. Okay, now we come to exercise 6, which is quite a technical little detail here. Let me just review what we did up here. I calculated the work done in moving a mass from a distance r away from the planet. If we move that mass all the way out to infinity, then this is the amount of work done, this positive amount of work done. And if I added that energy to the system in order to take it all the way out to infinity, where potential energy is 0, then when it was a distance r away from the planet, it must have had this amount less of potential energy, so that if it's 0 at infinity, I take away that amount, and then I end up with the potential energy function minus gmm over r. So that's kind of the way I like to derive this formula. But you could, of course, argue that, well, wait a second, if I bring the mass from infinity to the point, I'm sort of pulling back on it, but it's moving towards the point, so my work done is actually negative, and you sort of get negative gmm over r. You get that straight away with the negative sign. So, I mean, it's the definition is correct, and it kind of makes sense, but in understanding all this to begin with, I like calculating the work done in pulling the mass outwards, because then we just get a positive amount of work, and then I sort of later on say, oh, wait a second, well, if it's 0 at infinity, we need to take away this work to get the potential energy at the point. So yeah, just to let you know that the IB definition is the same as what we did above, and you should really write down this on your exam paper. Okay, next topic is escape velocity and orbital energy, one of my favorite topics. And we're going to answer the question, when a mass is launched from the surface of the Earth, how fast does it need to go to completely escape Earth's gravitational field? We want it to be able to leave Earth completely. So the minimum speed at which this happens is called the escape velocity, and we can just use the conservation of mechanical energy to work it out. So start off by looking at the total mechanical energy at the surface of the Earth. It has kinetic energy at its launch. It has gravitational potential energy. And if it has to make it all the way out to infinity with 0 speed, right? So we want the minimum amount of energy. We don't want sort of any excess kinetic energy out at infinity. The total mechanical energy at infinity is 0, potential energy 0, kinetic energy 0. And then we just use energy conservation. Just write down half mv escape squared plus the potential energy function, which is negative, has to equal 0, and you can rearrange that to get the escape velocity, root 2gm over r. Notice how it's independent of mass, also independent of the direction of the launch. So that's why we sometimes just call it escape speed instead of escape velocity. Okay, so a few exercises here. Okay, so first exercise is escape velocity at the surface of the Earth. Relatively straightforward, just plug in G, plug in mass of Earth, and you put in the radius. Remember to get it in meters. If you do that properly, you should get around 11.2 kilometers per second. Okay, pretty fast speed. So that is sort of the speed you have to launch something with at the surface of the Earth if you never want it to come back again. Okay, very high velocity. What about the surface of the Moon? So what do we need to change here? Just the mass of the Moon, radius of the Moon. If you do that, you get something like 2.3 kilometers per second. Bit easier to escape the Moon's gravitational field. And then what about the Sun? Well, we would expect that to be higher. Sun is more massive, much more massive. So plug in the values for the Sun. You can look them up. Mass of the Sun, look it up online. Radius of the Sun, you get something like 617 kilometers per second. And some of you might remember from our space science course that we actually measured the speed of a coronal mass ejection from the surface of the Sun, and they have speeds of around 500 kilometers per second. So you can see that's very close to the escape velocity of the Sun. So these coronal mass ejections, they can reach very far out into the solar system. Exercise 3. If Earth's radius suddenly halved in size without changing the mass of the Earth, how would that affect the escape velocity from the new surface of the Earth? Okay, so you can see that escape velocity is proportional to proportional to 1 over square root of the radius. Yeah, you can see that from the formula. So if Earth suddenly halved in size, the radius would be half as big. Okay, and then hopefully you can see, well, if you replace r by half r, right? So if I were to say r is replaced by half r, I get square root 2, 1 over square root r. So the escape velocity is going to be a factor root 2 larger, okay? So like the new escape velocity at this smaller Earth is going to be square root 2 of the old escape velocity. Multiply the 11.2 by square root of 2. Okay, so if I were to just visualize that, let's see. This was the old surface of the Earth. Earth sort of compressed into an Earth that has half the radius. Well, then the escape velocity at the surface there is going to be root 2 times the previous escape velocity. At the old surface, the escape velocity is still 11.2 kilometers per second. It really depends just on the distance. How far away are you from the center of the planet? That's really what determines the escape velocity from that point. Okay, what if Earth's radius suddenly became 100 times smaller? Okay, well, then hopefully you can see that if r is 100 times smaller, we get a factor root 110 times, right? So the new escape velocity would be 10 times greater, not 11.2, but 112 kilometers per second, etc. And then what would happen if Earth's radius kept on decreasing without changing the mass? Just r kept on getting smaller and smaller. Well, hopefully you can see that the escape velocity would start just increasing and increasing at that new surface, right? So it's kind of like the deeper you go in a gravitational well, the harder it is to escape it. The faster you need to go, the faster you need to be moving in order to escape the gravitational field. And let's try and do a fun calculation then. Well, nothing can travel faster than the speed of light in empty space. So how large should Earth be for the escape velocity at the surface to be the speed of light? So let's try and do that. So we have the escape velocity formula, which is root 2gm over r. Now let's put the escape velocity equal to the speed of light c. And then let's rearrange this to isolate r, the radius. And you get this interesting formula. And let's try and calculate this radius. So it's 2 times g and m, mass of the Earth. So you've got the mass of the Earth compressed into a very small radius. Has to be very small if the escape velocity has to be the speed of light. So let's just plug in the speed of light as 3 times 10 to the 8 meters per second. And how much is that? Okay, so what you get if you do this calculation is you get 9 millimeters. Okay, wow. So that's how small Earth has to be in order to have an escape velocity equal to the speed of light. You have to take the entire Earth and then compress it into a sphere that has a radius less than 1 centimeter. Then not even light can escape the surface of the Earth. And what you actually just created is a black hole. Okay, so that's how dense black holes are. You've got the mass of the entire Earth within a 1 centimeter radius. And this is what can happen to very heavy stars when they collapse under their own weight. Then we can create densities as large as this, and then black holes are created. And they're black because not even light can escape those objects. Okay, what we want to do now is we want to look at a situation where we have a satellite orbiting a planet. So let's just draw that. So imagine you have a planet, and then you have some satellite, mass m, that is orbiting. So it has some speed, some velocity there. It's going around in uniform circular motion, orbiting that planet. Okay, we can write down Newton's second law for this situation, ma equals F net. The acceleration is v squared over r, the acceleration in uniform circular motion. The force is the gravitational attraction. And from that equation, we can just cancel out a couple of things, and then we can rearrange to get the orbital velocity. So the orbital velocity is root gm over r. That's one expression that's in your data booklet. And we can then use that to, for instance, work out the kinetic energy of this satellite. So half mv squared, if I insert the orbital velocity, then I'm going to get half gmm over r. So I get this expression for the kinetic energy, kind of like the orbital kinetic energy. It is just half mv squared, but I express it in this way. Remember, the potential energy is minus gmm over r. And then we can work out what the total mechanical orbital energy is for this system. Kinetic energy plus potential energy, and you get negative half gmm over r. So these three expressions are really important in orbital mechanics, and we're going to be using them quite a lot when we solve problems. One really good way to remember these expressions is to think of their graphs, okay, which I'm showing here. Now, kinetic energy is always positive. You can see how kinetic energy is proportional to 1 over r. It's a hyperbola. So I've drawn a positive hyperbola there, the kinetic energy. Total energy turns out to be negative the kinetic energy. Okay, still a 1 over r dependence, but it's negative. So it's just a mirror image of the kinetic energy, right? So Ke, mirror image of total energy. And the potential energy is minus gmm over r, so it's actually minus 2 times the total energy. So you can see it's 2 times lower than the total energy. Okay, so that's a relationship you should really remember. Try and internalize these graphs. They're going to be very useful. Okay, yeah, let's do some exercises. And how many times greater is the escape speed compared to the orbital speed? Well, you can, just by comparing those two formulas, you can see that the escape velocity really is just square root 2 times the orbital velocity. Nice. Let's imagine some planets orbiting a star. Which planets have the greater orbital speed? Well, we can see that kinetic energy decreases with distance, so the further out you are in orbit, the slower you are moving. Okay, so it's the planets that are far away that are moving slowly. Outer planets are slower. The inner planets are faster. Mercury is like the fastest planet, the innermost planet. Neptune is the slowest planet, the one farthest away from the sun. This is, notice how this is different, so not the same as a solid spinning disk. So maybe you can remember from circular motion that we talked about how if you have like a solid spinning disk with one constant angular velocity, then when you move further away from the center of the disk, then parts of the disk are moving faster because they have to travel a longer distance in the same amount of time. Well, this is kind of the opposite of that, right? Because here we don't have a solid disk. We just have gravity holding onto these planets, and the further away they are, the slower they move in their circular orbit. Okay, and then we come to the hardest thing to understand, the satellite paradox. So that has to do with, say, when something enters our atmosphere, for instance, enters our Earth's atmosphere. We have, rocks and small pieces of metal from spacecrafts that sometimes enter our atmospheres, and they sort of burn up in the atmosphere. And when they enter the atmosphere, we sort of have a drag force that does negative work on the object. Okay, so it kind of takes away energy. But does it actually slow down, right? That's what we're used to thinking of when a block slides across a table. Friction sort of slows it down, takes away kinetic energy. Well, in this case, it's a little bit different because, and let's look at the graphs here. So say you are in, say this chunk of rock or metal is in orbit around the planet, has a certain amount of total energy. If it now starts to experience a drag force, it's going to lose total energy. So it's sort of going to slide down the total energy curve, but that actually corresponds to an increase in kinetic energy. It actually speeds up. And how is that possible? If it's losing sort of total energy, negative work is being done, how come it's speeding up? Well, that's because we have to remember gravity's there. And when it loses total energy, it moves closer to the planet, which means it also loses potential energy, and it loses more potential energy than total energy. So that in order for all the energy to balance out, it actually needs to increase its kinetic energy. So that's a little bit confusing. It's called the satellite paradox, that even though there's a drag force doing negative work on something, it actually speeds up because it's also falling closer to Earth and losing even more potential energy. The satellite paradox is also the reason why meteors, they sort of burn up so quickly in the atmosphere, because as it falls closer to the surface of the Earth and it speeds up, then the drag force actually increases. So it heats up the meteor, the rock, heats it up more so that it burns up quicker. So that's why sort of meteors, they sort of burn up as they do in the atmosphere. Okay, now we're going to talk about the gravitational field potential. Not the potential energy, but the potential. Very confusing. Recall that the gravitational field strength was the force per unit mass at a point in the field. Now we've talked about there's gravitational potential energy, so we could also talk about kind of the gravitational potential energy per unit mass at a point. So that's what the gravitational potential is, right? That we know that, okay, Earth creates a gravitational field. If I were to place a mass in the field, there would be gravitational potential energy. But I can also imagine that little mass removed, and I can talk about the gravitational potential energy per unit mass at that point. So that's what potential is. Gravitational potential is the potential energy per unit mass. And you can see that the little mass cancels out, so you just get minus gm over r. Okay, you don't get minus gmm over r, just minus gm over r. So that also leads to this important relationship that, to get the potential energy, I just need to take the potential and multiply by the mass, okay, mv. This is often written as delta PE is m times delta V, because we're often always looking at changes in energy and changes in potential. Okay, so why do we introduce this new quantity, gravitational potential? Well, the big advantage is that potential, like potential energy, is a scalar quantity, and it's easier to work with scalar quantities. So, for instance, we saw earlier that if we sort of add fields, if we have multiple fields present at the same time, then we can determine sort of the net field strength vector by doing vector addition. But vector addition can be a little bit complicated. But when we're just adding potentials, then it's much easier because we're just adding simple magnitudes together. And you'll see the advantage of that when we start doing some problems. Okay, the first exercise is, what is the unit of gravitational potential? Well, if potential is energy per unit mass, then obviously the unit is going to be, well, the energy of potential energy, which is joules, over the unit of mass, which is kilograms. So joules per kilogram, that's the unit of gravitational potential. Okay, let's calculate the gravitational potential at the surface of the Earth. So that's V is minus g m over r, where r is the radius of the Earth. So we plug in all the usual numbers. By now you definitely should be knowing all these numbers by heart. Earth's radius in meters, right? And then what is that equal to? Minus 6.3, 10 to the 7 unit joules per kilogram. Okay. Now this shouldn't, okay, let's talk about that later. So what about Earth? For the Earth, calculate the gravitational potential at the moon's distance. Okay, so same formula, we're just plugging in again. But now we are looking at a distance that is 3.84 times 10 to the 5 kilometers, convert to meters. So we get the right unit, plug it in. You get something like, what do we get? We get something like around -1 10 to the 6 joules per kg. That's the potential due to the Earth at moon's distance away from the Earth. Graph the variation of potential with distance. Okay, what's the name of this mathematical curve? I think you're starting to get the idea here that, okay, potential is also inversely proportional to distance, proportional to 1 over r. So we also have a hyperbola like that. If we start at the surface of the Earth, we have the potential in units of 10 to the 7 joules per kilogram, start at -6.3, and then it sort of just increases according to that curve. You can click on my Desmos file to sort of explore that graph, or you can just graph your own. What is the change in gravitational potential when you move from a distance of 2 Earth radii to 5 Earth radii? Okay, well, hopefully you can see, well, that is, again, just doing the same as we did before almost. It's the final potential minus the initial potential. So it's negative gm over 5r minus gm over 2r. I'm going to take gm over r outside, 1/2 minus 1/5. I actually haven't worked this one out yet. So, oops, let's do that quickly together. 6.67 times Earth's mass divided by Earth's radius times 1/2 minus 1/5. And I get something like, let me see, did I do that right? Yes, I get a positive quantity. Good. I got a positive quantity, but it has to be positive. It's a positive change. We're moving away. So what's that? 1.9. 1.9 times, what is it? 10 to the 7. You look at your calculators too, people. Joules per kilogram. Okay, increase in gravitational potential when it goes from 2 to 5 Earth radii. And of course, it's opposite. If we go in the opposite direction from 5 to 2 Earth radii, then there would be a decrease in potential. Okay, now hopefully you can see that all these questions have something to do with the previous questions we did for potential energy. And how do they compare to the previous ones we did? Well, we know that potential energy is just mass times potential. So I can get all the answers to the previous problems by just multiplying by the appropriate masses. Okay, so for instance in B, if I'm just looking at B, if I want to find the gravitational potential energy of the Earth and the Moon system, I need to take this potential and multiply it by the Moon's mass. And then I'm going to get the answer to the previous question, the gravitational potential energy of the Earth and the Moon. So that should make sense, hopefully. Now, F says the Moon has this mass. Okay, that's the mass to 2 sig figs. What is the net gravitational potential halfway between the Earth and the Moon? So this is an important one. So let me draw it. Here we have Earth. And here we have the Moon, not to scale. and we have a distance which is, what is it, 3.84 times 10 to the 8 meters. Okay, now we're looking at a point right halfway between them. What is the net potential? Well, this is where it's very convenient that potential is a scalar quantity. So we can talk about how, well, the potential at that point due to the Earth is equal to this, where I just take that distance over 2, right? So just the minus gm over r, where r is sort of half the distance. But then there's also a potential at that point due to the moon. 3.84, 10 to the 8 over 2. And what I do is I just add those two scalar quantities to get the net gravitational potential at that point. So net, right? Let me just tell you that V1 is something like minus 2.1 10 to the 6 joules per kg. V2 due to the moon is much smaller. So it's like minus 25 10 to the 3. So moon's potential at that point is much smaller than Earth's potential. So when I add these two together, actually the potential due to the moon is insignificant. And I'm just left with also negative 2.1 10 to the 6. But this goes to show how it's easier to work with potentials with just adding numbers rather than doing vector addition. Okay. Graph the net gravitational potential due to the Earth and the moon as it varies from the distance of the Earth. Okay. Okay, so we worked out the net gravitational potential halfway between them. Okay. But what if we try and work out the net gravitational potential at any given point along this line? Well, then I just need to add potential functions. Okay, so let me show you how we can do that. So do it like this. So we're looking at the Earth and the moon again. Let's say we're looking at a point here that is x away from planet Earth, right? Well, then I know that this distance from the point to the moon is going to be 3.84 times 10 to the 8 meters minus x, okay? And then I can say, well, I've got V1 minus g mass of the Earth over x. That's the potential at this point due to the Earth. But I also have a potential V2 due to the moon at that point minus g mass of moon, and then it's 3.84 times 10 to the 8 minus x. And I just add those two together. And then I have something that's a function of x, and I can graph that. So let me show you what that looks like. Okay, so here you can see I've graphed the net gravitational potential due to the Earth and the moon. Okay, so I use those functions that I wrote down. Let me just show you, where are they? They were here, right? So I've got, whoops, what just happened? Okay, here we are again. That if I'm a distance x away from Earth, there's a potential minus g mass of Earth over x. And at that point, I am 3.84 10 to the 8 minus x away from the moon. So there's a potential at that point due to the moon. And if I just add those two together, I get this. This is the net gravitational potential. Just to show you the individual potentials, there's the Earth's potential. There is the potential due to the moon, and I just add them together to get the net potential, which looks like this. So very easy to work with this scalar quantity. We just add them together. Okay, exercise 3. We are looking at the Earth. And I want to draw circles with Earth at its center, radii 2, 3, 4, 5 Earth radius. Okay, so that's going to be roughly, I'll try my best. That's a circle 2 Earth radii of radius. And then I have 3. And then I have 4. Okay, you can all see these are perfect circles. And then I want to calculate the gravitational potential at points on these circles. Okay, now let's sort of label them, shall we? Maybe V2 for the circle that has 2 Earth radii, V3, V4, V5. And we can calculate the potential at points on these circles. So V2, for instance, is around negative 3.1, 10 to the 7 joules per kilogram at any given point on this circle, because all the points on this circle, they have the same distance away from the Earth, so they all have the same potential. So this is called an equipotential line, corresponding to negative 3.1 times 10 to the 7. Okay, V3. So on the circle given by V3, that's also an equipotential line. The potential at any given point on that circle has this value. Likewise, V4 minus 1.6, V5 negative 1.3, 10 to the 7. Okay, so these circles are called equipotential lines because points on those circles all have the same potential. Now, of course, you have to imagine these circles are really spheres in 3 dimensions because we live in a 3-dimensional world. So we also sometimes refer to these as equipotential surfaces. Okay, then the last question says, draw some gravitational field lines. So let's remember gravitational field lines, that they look like this, the field lines surrounding the Earth. Okay, sort of this radially symmetric field, and the closer we come to the Earth, the stronger the field is. Then it says, notice that the field lines are perpendicular to equipotential surfaces. Can we justify why that is always true? Look at these field lines, they're perpendicular to these circles. Why is that true? Well, it's true because when you move along one of these circles, right, for instance this circle, if I'm moving along this circular arc, then the force of gravity is always perpendicular again to the displacement, so no work is being done by gravity, so I'm not changing the gravitational potential energy, which means I'm not changing the gravitational potential. So that's why field lines, they always are perpendicular to equipotential surfaces, because the potential energy doesn't change on a equipotential surface. Okay, now we're going to cover the last concept for today, and that is the relationship between potential and field strength and potential energy and force. So let's start looking at this picture of a mountain and a map showing some contour lines on the mountain. So contour lines are actually equipotential lines because they correspond to points that have the same potential energy because we're the same height above the ground. So you can see here we're looking at height, say perhaps 10, 20, 30, 40 meters above the ground. And the contour lines, they all have the same potential energy, so they're equipotential lines. Okay, now if we take a look at a mountain where we have drawn contour lines for sort of a constant increase in height, you say we're going up by 10 meters again over here, right? So every increase here is like 10 meters, drawing all the contour lines. Well, you can see when the contour lines or the equipotential lines, when they're close together, then the mountain is very steep, and gravity is sort of exerting a large force down the slope there, whereas when the equipotential lines are further apart, then the mountain is not so steep and gravity is less strong, like exerts less force down the slope. So it's when contour lines are close together, you have a strong force. When they're further apart, then the force is weak. And we can sort of quantify that in the following way. We can sort of imagine we have a big mass, say the Earth, and we have a little mass that we are, pulling away from the Earth. Say we're pulling in a small distance, delta r, so small that the force is roughly constant along that displacement. Well, then the change in potential energy is the work done by that force, F times delta R. But I can then divide both sides by mass, and I get the change in potential energy per unit mass, but that's just the change in potential, and I get force per unit mass times delta R, but force per unit mass is just G times delta R, and then I can divide by delta R on both sides, and we can see that, oh, wait a second, G, gravitational field strength, is the rate of change of potential with distance. Okay, here we sort of just have the magnitude, you could say. Magnitude is the rate of change of potential with distance. If you actually want to include the direction, then you can be a little bit more careful. You can add a negative sign because we know that G always points towards the planet. That is opposite to an increase in gravitational potential. When we move away from the planet, V is increasing, but G is pointing in the opposite direction. That's why we have that negative sign. And let's see what that means graphically, right? So basically, if we go back to this really important graph, we can see this is the net potential in the Earth-Moon system. Okay, this is a graph of V, the potential. So if I want to now know what is the magnitude of the gravitational field strength at various points, well then I simply just have to draw a tangent at that point and find the slope to get G. So if I want to find what is the magnitude of G at a distance 1 × 10⁸ meters away from the Earth in this Earth-Moon system, remember we have sort of the Earth over here, we've got the Moon over here. Well, then I draw a tangent to my best ability, find the slope of that, then I have the magnitude of G. If I put a negative sign on it, then I know it's pointing to the left towards the Earth. Likewise, if I go sort of twice as far away, you can see that the slope decreases, G decreases. There's this interesting point over here where we can see that, oh, the slope of the tangent is 0. At this point, we have a net gravitational field strength that is 0. We actually talked about that point earlier in the lesson. That is where the two G's, the gravitational field strength due to the Earth and the Moon, they are equal in magnitude but pointing in opposite directions. Now we can identify that point here by looking at a horizontal tangent for the potential graph. Okay, so that's how that works, and we are finally done with that lesson, and that means you are ready to work on a lot of problems now. I have one quiz for you to take, and then I have a bunch of past IB exam papers that we can work on in class. Okay, see you in class.